Alright students, this is I think a really good example of an area or volume type question on an AP test. I think it has all the pieces, even though they're not very tricky or tough ways of doing these. So we're going to go through each piece. This is also a really good example of how using your calculator effectively can save you a ton of time. We're going to go through that too. So here's the question. R is this chunk right here, bounded by sine on top, and then 1/2 on the bottom. It's just the chunk in between those two things. So the first question says find the area of R. Anytime you're thinking area, think top minus bottom. Always top minus bottom. But we actually don't know these intersection points. You could solve this by hand. It's like, when is sine 1/2? At pi over 6, right? But let's do it on our calculator so we have it and so that we can save that value. So I've graphed this. Let's see how this shows up. I graphed this on my calculator on one of the lenders. Some rascal drew all over it. What the heck? And I used the window from the problem. So like, I see that the x value goes from -1 to pi, or like 0 to 3.14. So I go from -1 to 4. And then my y, I went from -1 to 2. So look at the graph shown. Adjust your window if necessary, and then match that on your calculator so you have a pretty good idea of what this actually looks like. So here's my graph. Second calc intersect. Go over to that intersection point. Hit enter, enter, enter. There it is. Save this. Let's save this value. Here's how you do it. I like to get out of here. You can just hit store on some calculators, and then, sorry, store was down here, STO, and then save it as any letter. So I'm going to do alpha, and I'm going to save it as, well, I like to use C for Connor, but we'll just use A in this case. Enter, store, A. There it is. If your calculator, if you hit store and it doesn't come up, that's because your calculator doesn't know what it's trying to store. Your x variable stores the value for one problem until you use it again. So right now x is that same number. So if you hit store and nothing came up, you can do x store a, and it'll store that same value. Once you find the second intersection point, so let's go back to our graph, second calc intersect, all the way over here to the second one. Enter, enter, enter. There it is. Now x is saved as this x value. So we can get out of here, and then we can do x store b. So now I have my two limits stored as a and b in my calculator, and I can integrate from a to b really easily. And I can use y1 and y2 because I have those functions saved as y1 and y2 in my calculator also. So let's write this out. Part A, find the area of R. Area is, oh, I should write down A and B, right? So my intersection points, A from my calculator was 0.523599, and B was 2.617994. Make sure you write those down somewhere, because now when I do my integral, it's from A to B, and top minus bottom in terms of x. It's probably 1 point to find those intersection points, 1 point to write this integral, and then 1 point to evaluate it on your calculator. So I'll do math 9, integral from A to B, and sine of x minus 1/2. But again, instead of that, let's do it with the functions. Sine of x is stored in y1. So I'm going to say vars, y vars, and then hit 1 for function, and it's option 1. So my y1 function is right there. I'm going to do the same thing, vars, y vars, function, y2, dx. Hit enter. here is my area, I hope. For some reason that looks wrong to me, so I'm going to just check the key real quick. 0.684. Let's see, this was question 2. Oh, thank goodness. I was worried. Okay, so this is approximately 0.685 units, whatever. I can't label these as y1 or y2 on my in my equation because I haven't named them anything. I could rename them if I wanted, but I'm not going to do that. Part B, if I'm revolving around the x-axis, remember, here's kind of our hint, pi times integral from a to b of big R squared minus little r squared dx. I'm not going to keep this as is. I'm going to kind of cross this out because I already have an r here, and if I use it here, that could be confusing for the College Board. So this is just a little note for myself, and now I'm going to scratch it off. Pi times the integral from a to b, my big R radius, the one that's further from that axis of rotation, is my sine function. And so that's the first term. What am I doing? That's the first term that I'm going to write, and the first term I'm going to square. Sine of x squared minus 1/2 squared dx. Anytime I have rotations around an axis, it's got to be pi r squared minus pi r squared. So let's plug this into our calculator. There's actually a really similar integral. So pi times the integral from math 9, integral from a to b, and now we'll do varies y varies function y1 squared minus varies y varies function y2 squared dx. I never taught anyone how to do this until this year, so if this isn't working for you, don't do it, just type the function. But I do think this could be a way to save some time. Hit enter, 3.005. It does say write and evaluate, so we definitely need to do that. And then the last one, hey, they are semicircles. So we got a cheat sheet here for the semicircle situation. We usually always say, top minus bottom. Semicircle constant is pi over 8. So for integral from a to b, there's a lot of screaming going on out there. What the heck, Robot Club? Integral from a to b, pi over 8 out front, and instead of squaring each one individually, we're going to square the difference. This is kind of just a rule. It would take a long explanation to prove it without a nice picture, without some sketching. We could sketch that out. We could write a different integral for the semicircles, but I think we should just remember, write the formula for the square, that's this chunk, as if they're square cross-sections. That's what I'm saying here, cross-sections. Write it as if they're square cross-sections, and then multiply by pi over 8 to become semicircular cross-sections. So this is, again, a very similar equation to plug into your calculator. Pi divided by 8 times math 9 from a to b. But now instead of y1 squared minus y2 squared, it's y1 minus y2. And then square the difference in terms of x as our integration. 0.107. Again, I think all three of these pieces are very good examples of maybe a slightly simpler example than what you would see on an AP test, but the kinds of things that could be asked. So that's all I got for this one. Good luck practicing. Keep it up. You can do it.